Ever wondered why some AI models master their training data, but fail in the real world? Why adding more layers or parameters can sometimes backfire? Today, we're unpacking a groundbreaking paper that uses physics, math, and a dash of creativity to demystify how machine learning models actually work. Let's dive in. Imagine teaching a computer to recognize cats in photos. You feed it thousands of images, and it starts picking up patterns: fur, ears, whiskers. But here's the twist. If the model is too simple, it misses the big picture. If it's too complex, it memorizes every photo instead of understanding what defines a cat. This tension between simplicity and complexity is the bias-variance trade-off. But what if we could visualize it as a landscape? Enter the loss complexity landscape. Picture this as a map where the x-axis represents model complexity, number of parameters, architectural depth, and the y-axis is loss, how inaccurate the model is. The goal? Find the sweet spot where the model generalizes perfectly. No overfitting, no underfitting. But how do we measure this? Here's where the research gets fascinating. They borrow concepts from physics and information theory. They use the Kolmogorov structure function, a mathematical tool that quantifies how much information a model needs to describe a dataset. But since true Kolmogorov complexity is uncomputable, they create a practical proxy that still captures the essence. Think of it as a GPS instead of a hand-drawn map, less precise but wildly useful. Now here's the breakthrough. They draw a parallel between machine learning and statistical mechanics, the physics of systems with many interacting particles. Model complexity and loss become forces in a system. They define an information-theoretic action, a mathematical formula combining both, like a cost function for the model. By minimizing this, they derive a free energy functional, a concept from physics that balances energy and entropy. This leads to a key insight. The relationship between complexity and loss follows a Legendre-Fenchel duality, a mathematical symmetry akin to a seesaw. Tweaking one side complexity, adjust the other loss. And just like in physics, where systems undergo phase transitions, like water turning to ice, the paper shows models have critical points where overfitting spikes abruptly. These are the phase transitions in the loss complexity landscape. To test this, they ran experiments with models like linear regression and decision trees. And guess what? The theory matched the data. They found that as models grew more complex, their loss curves exhibited sharp transitions, proof that the physics-inspired framework isn't just theoretical. So what does this mean? It gives us a new lens to understand why models fail, how to design better architectures, and when to stop adding parameters. The next time you tweak a neural network, remember, you're not just adjusting numbers, you're navigating a physical-like landscape of complexity and error. Thanks for watching. If you want to dive deeper into the math or explore the experiments, check the links below. Stay curious and keep pushing the boundaries of what AI can do.